In this video, we're going to talk about the logic of an ANOVA. ANOVA stands for Analysis of Variance. So that's why whenever you see it written, you always see it written in capital letters because it's an abbreviation. As always, the logic of ANOVA starts with sampling. You have to take a sample because you cannot study the entire population. ANOVA is typically used when you are trying to conduct a study with 3 or more groups. So you take the sample and you break it up into different groups. In this case, I'm just using 3 different groups. As before, the best way to put people into groups is through some kind of random assignment. The point here is to try and get 3 groups that are initially equivalent. They're about the same before you do anything to them. Then you give each group its respective treatment. So group 1 gets treatment 1, group 2 gets treatment 2, and group 3 gets treatment 3. These could be 3 different treatments, or one of them could be a control condition. Doesn't really matter. You're just treating the 3 groups differently. After you treat them, you get the mean from each group. And of course, the logic here is that if the treatments are all equally effective, these 3 sample means should all be similar. And that's what this is going to tell you here. All 3 means should be similar if the null hypothesis is true. The 3 treatments are equally effective. The 3 sample means should be about the same. Of course, they might differ due to sampling error, and that's why we need a significance test. How far apart do these 3 means have to be in order for us to be confident that it's not sampling error? Well, of course, the research hypothesis is saying that the null is not true. And in order for us to reject the null, it just has to be the case that any one of these 3 means has to be different from any one of the others. Now, when you've got 3 means, there's actually 6 comparisons that are possible here. You've got 1 and 2, 2 and 3, and then 1 and 3. Excuse me, 3 comparisons that are possible here. These 3 comparisons, if any one of these 3 comparisons are different, you would reject the null. It could be that they are all different. This is different, 1 and 2 are different, 2 and 3 are different, and 1 and 3 are different. Or it could be that just any one of these 3 comparisons are different. Okay, now we're going to start talking some conceptual stuff here. There are 3 different things that contribute to variance or differences among scores and groups. The first is measurement error. There will always be measurement error, no matter what you're measuring. Depression, cholesterol, head size, no matter what you're measuring, there will always be some type of measurement error. You can never measure something perfectly. The second contributing factor to variability is individual differences. People are different. One person is going to have a different score than another person just because of natural variability of things. This is true of people. This is true of plant seeds. Things are different. There's just individual differences among things that we do experiments on. The third thing that can influence scores in groups or scores among individuals is a treatment. If a treatment is effective, it's going to, and people get different treatments, that's going to produce differences among the scores. So these are the 3 things that can cause differences among scores. The first 2 things are really, you might think of conceptually as, quote, bad variability. That's variability that researchers are interested in trying to control. The third treatment effect, third source of variability, that's what researchers are really interested in doing an experiment to figure out. how much of the variability is created by treatment effect. So, as I've said, the first two are bad variability. In the past, we've referred to these two things as sampling error. Both of those factors contribute to the amount of sampling error in a study. All right, now I'm going to talk a little conceptual formula here. Now, this is not, repeat, not a mathematical formula. It's a conceptual formula. It's how the ANOVA works to eliminate the bad variability, and so that we have some index of how much good variability, how much treatment effect is left over after we eliminate all of the sampling error. So it's the treatment effect, F. F is the symbol that we use for ANOVA. Now, why does F signify ANOVA? Well, the person who came up with the ANOVA statistical approach, his name was Fisher, and so we call this an F test. That's why whenever we're computing ANOVA, the symbol will be F. The numerator of ANOVA is one number, and that one number has three things in it that contribute to the size of that number: the treatment effect, individual differences, and measurement error. So that one number on top has those three things contributing to it. The problem is we don't know how much of that one number is due to any one of those factors. So if the number on top is 10, we don't know how much of that 10 is created by the treatment effect, the stuff we care about, or individual differences and measurement error, the stuff we don't really care about. That's why we need the denominator. The denominator has in it individual differences and measurement error, the stuff we don't care about. There's one number on the bottom as well, one number that represents sampling error. If that number is 5 and the top number is 10, what we do is we take the denominator and divide it into the numerator, and in theory what happens is the bad variability cancels out, and what we're left with is just the good variability that we care about. That's the logic of ANOVA. We want to cancel out the bad stuff, so we're left with just the good stuff. Okay, now we're going to go through a more concrete example. Here is some raw data. Group 1 has 3 people in it, and these are their scores. Group 2, 3 people, those are the scores. Group 3, 3 people, and those are the scores. Now, let's just say that this is Bob. Bob got a score of 5. This is Susan. Susan got a score of 7. Why aren't those two scores exactly the same? They were both given treatment 1. They're both in the same group, so they were both given treatment 1. Why aren't they exactly the same? What causes variability within a treatment condition? Why are these scores different? Well, the reason why those scores are different is because of individual differences and error. Individual differences and measurement error are the two things that contribute to within treatment variability. Again, within group 1, not everybody has the same score. The only thing that could be making them have different scores is measurement error and the fact that people started off not exactly the same because of individual differences. Well, that's exactly true in group 2 as well, right? And that's exactly true in group 3 as well. Variability within those conditions is due to individual differences and error. Now what we're going to do is we're going to compute the mean within each condition, and that's what I've just done here. The mean of group 1 is 7, the mean of group 2 is 7, and the mean of group 3 is 14. Now, these aren't all the same, right? The difference between these two scores is 0. I should say the difference between those two means. The difference between these two means is 7. And the difference between these two means is also 7. So not all of the scores are the same. There is some variability in these scores. Well, what's contributing to the variability of these means? What's contributing to the variability of these means? Well, the obvious thing is that the people in group 1 were given treatment 1, the people in group 2 were given treatment 2, and the people in group 3 were given treatment 3. So part of the variability across these conditions is due to the treatment. However, there's something else also contributing to these means, right? Just like these people within group 1 are different from each other, it's also true that these people in group 2 are different from the people in group 1, right? And also different from the people in group 3. So these means are contaminated with individual differences and error. These means are also have in them individual differences and error. So between treatment variability has in it the good stuff and the bad stuff. Variability within condition just is, quote, the bad stuff. And so to create an F value, what we do is we take the variability between and divide that by the variability within. Remember that the variability between has in it individual differences and error and the treatment effect. Variability within has in it individual differences and error. So conceptually what we're doing is we're going to cancel out the bad stuff in the numerator with the bad stuff in the denominator. And what we'll be left with is just the treatment effect. Now again, that's a conceptual formula. We can't do that mathematically. So we have to do it in a slightly different way. And what we're going to be doing is we're going to be creating something known as a mean square between treatment. Now this little bt there is supposed to be a subscript. That's the mean square between treatment. It's sort of the average variability across the different groups. And the mean square within treatment, that's sort of the average variability within the treatments. So this is sort of the average error variance or average sampling error. And this is the average treatment effect. And by dividing the average error into the average treatment effect, we're going to end up with one number that indicates the size of the overall difference among the different treatments. And if that is big enough, we're going to reject the null. All right, let's walk through this one more time with I guess in a little more detail. Here's the same data that we used on the previous screen. And now what I'm going to do is I'm going to fill in a source table. You're going to be working with source tables for this chapter and the next chapter. It's really important that you understand these source tables because they sort of will walk you through how to conduct the ANOVA, and they'll help you interpret the ANOVA at the end. So I'll start filling it in with some data here. This column right here is called the source column. And under that source column, there are the different types of variability that the ANOVA analyzes. BT stands for between treatment variability. Again, between treatment variability has in it individual differences, error, and the treatment effect. So this number 98 has good stuff and bad stuff, and we want to strip away the bad stuff. Now, the size of this 98 is influenced by, again, how different scores are within conditions, bad stuff, and it's influenced by how different these means are from each other. The more different these means are from each other, the bigger this number 98 would be. So like if I were to just change one of these scores, maybe make this score 10 rather than 7, now there's more variability among those means. This 98 would now be a higher number. I'm not interested in showing you how that 98 is computed right now. I just want to talk about conceptually what's going on. So this number is going to be bigger the more different these means are. Okay? This number, the within treatment, is influenced only by the within treatment variability, the within group variability. So the only way that's going to be bigger is if we have more error in measurement or we have more individual differences. That's just the bad stuff. The total is just summing up the between treatment and within treatment. Now, this column is the sum of squares column. And again, you'll learn how to compute those. But right now we just want to talk about conceptually. They're measures of variability. They're measures of types of variability. Now what I want to do, that's a sum of squares. And I want to get, as I've indicated, the mean or average amount of variability for between treatment and the average amount of variability for within treatment. And so like always, when we have a sum and you want to get an average, we need to divide by something. And what we're going to divide by is the degrees of freedom. Well, the degrees of freedom for the between treatment is the number of groups minus 1 is going to give us 3 groups minus 1 is going to give us 2. That's how we get the DF for 2. If we had a 4th group, then it would be 4 minus 1 and we have a DF of 3. But it's just 2 in this case. Now we need to compute the DF for the within treatment. That's going to be 6. And the way you would get that is it's N, which is the total number of people in the study. There was 9. 1, 2, 3, 4, 5, 6, 7, 8, 9 people in the study, minus the number of groups. There was 3 people, or 3 groups. So it's going to be 9 minus 3, and that's going to give us 6. As I said before, in order to get the mean squares, we are going to take this sum of squares and divide by the DF. So if we take the sum of squares, divide by the DF, we're going to get the mean square. So 98 divided by 2 in the first row, it's going to give us 49. 18 divided by 6 is going to give us 3. These are our mean squares. So this is the average variability due to treatment and individual differences and error. And this is the average variability due to individual differences and error. And so what we want to do is divide the 3 into the 49 to get F. And if we do that, we'll get 16.33 for F. That means that there is 16 times more variability than you would expect due to sampling error. That's a pretty sizable effect. The next thing to compute is our effect size. And the effect size we use for ANOVA is something called eta squared. And that's the little symbol here. It's kind of a funky looking N with a square. And technically, what we're actually computing is a partial eta squared, so there should be a little p subscript there. The way you compute that is you take the sum of squares between treatment, 98, and divide it by the sum of squares total. And if you take 98 divided by 116, you'll get 0.85. That's a very large effect. Anything above a 0.25 is considered a large effect. Anything close to, say, 0.09 is considered a small effect. We'll talk more about how to interpret the eta squared in the activity. Okay, so here is our obtained F value. Is that large enough to be significant? Is that more than we would expect due to chance? Well, we said it was 16 times more than we would expect by chance, which sounds like it's a pretty big effect. But is that enough? Our study was pretty small. Maybe it's not enough to rule out sampling error. Well, the way we do that is we have to look up a critical value. This is what an F curve looks like. You can never get a negative F. So the lowest score you can get on F is 0. If the null is perfectly true, you should get an F value of 1. Remember, if the treatment isn't doing anything, then you should get an F value of 1. So what we need to do is find the critical value. Where on this curve, how far to the right does our obtained value have to be in order to reject the null? Well, the way you do that is you look up a critical value in a new table. And you'll need to use the degrees of freedom. You'll need to use 2 degrees of freedom. You'll need to use 2, the DF for the between treatment. That will tell you what column your critical value is in. And the 6 will tell you what row it's in. So in Appendix C, in the back of the book, the critical values for F, you're going to find column 2, row 6, and you go over and choose the alpha value for 0.05. When you do that, you will find that the critical value is 0.54. That is our critical value. We got a 16, which is way out here. So it is in the critical region, so we are going to reject the null. That means that these 3 means are not the same. At least one of them is different from the other. Now in this case, it's obvious because this is the only one that is actually different. And we know, since these are the same, that this is going to be different from both of them. But in most situations, you're going to have to do what's called a post hoc test to determine which of these 3 means are different from each other. And we'll talk more about that in a future activity.